Hello and welcome. In this video, we're going to focus on some more specialized functions, recognizing them and understanding how to integrate them. And those special functions are exponentials, integrals that result in natural log, and integrals that result in inverse trig. So we're going to go ahead and start with a little warm-up just that has 3 integration problems that we should be able to do by reversing the chain rule or using use substitution and using natural log, which we already learned about in a previous lesson. So let's go ahead and jump right in. So here are those 3 problems. I'm going to encourage you to pause the video and work through each of these on your own and then unpause the video and see how you did. So here are those 3 problems worked out. The first one I think is pretty easy to see the reverse the chain rule on. You just need a scalar in the numerator of 3. So we can multiply by 3 inside the integral and we can multiply by 1/3 on the outside. But I did also show the use substitution steps. For number 2, you can actually just split that up into 2 fractions, integrate x squared over x, or just x, using the power rule, and integrate 4 over x, or negative 4 over x, is going to give you negative 4 natural log of the absolute value of x. The last one I think is a little harder to see the reverse chain rule, but you can use it there. You can also use use substitution and let u equal the denominator, which is going to give you du equals negative 3x squared, and you can work through it that way. Things to check over: make sure you have your plus c, make sure you have your absolute value with natural log, and if you did use substitution, make sure your final answer is back in terms of x. So let's talk a little bit about why absolute value needs to be a part of this antiderivative, needs to be a part of what we get when we integrate with these types of problems. So we know that the derivative of natural log of x is 1 over x, but we also know that natural log has a domain restriction. Natural log can only have inputs or x values that are greater than 0. The domain for natural log of x is that x must be greater than 0. The domain for 1 over x is just that x is not allowed to be equal to 0. So if we're going back and forth between these 2 functions based on the relationship that we know exists between derivative and antiderivative, we need to make sure we're not having a conflict of domain in either direction. So to remedy this, we just use absolute value. So whether that's just 1 over x, absolute value accommodates the fact that we can't have negative values. We could have negative values in this integral, but we can't in the function that we get out. If there's a u substitution situation and we have u prime over u, same thing. We need to have absolute value around that u as a function of x. So now that we've sort of solidified and done a good amount of practice with natural log, let's actually talk about exponential functions and how to integrate exponential functions that maybe aren't base e. So we learned previously that the derivative of e to the x is e to the x, which means that the antiderivative of e to the x is e to the x plus c. So just like we did with derivatives, we're going to go ahead and figure out what the integral of some other number to a power is using the change of base formula that we proved or we derived in a previous video. So we're going to start with this fact. If we're integrating b to the x, we can rewrite that as the integral of e to the x natural log of b dx. And this comes from the change of base formula. Well, we know that the integral of e to the x is e to the x, which means if there is a function in the exponent here, we just need to make sure that that scalar is inside the integral as well. And we can put that scalar there, right? Natural log of b is just some number, as long as we also divide by it out front. That means that this is going to simplify to be 1 over natural log of b times e to the x natural log of b plus c. But our ultimate goal was to figure out what the integral of b to the x was, and I don't think we want to have to convert to e every time. So what we know is that this is b to the x. So this is going to be 1 over natural log of b times b to the x plus c. So down here we have a summary of these sort of 4 different but very similar theorems. The integral of e to the x is e to the x plus c. The integral of e to the u times u prime is e to the u plus c, so u being a function of x here. The integral of b to the x dx is 1 over natural log of b times b to the x plus c. And if there is a function within that, we can use u sub and make sure that we have that u prime in front to get us over here as well. So what I'm going to encourage you to do is pause the video and try and use this shortcut to work through these two integration problems here. Okay, hopefully you've had time to pause the video. The derivative of that exponent is 1, so 3 to the x plus 4. The derivative of the exponent itself is 1, so we don't really have to worry about this u prime u situation, which means this is going to be equal to 1 over natural log of 3 times 3 to the x plus 4 plus c. Now on number 5, two things are happening here. The first is that we have bounds on our integral, and the second is that we do have a second function here. This exponent, the derivative of this exponent is 2x. So what I really want is a 2 here and a 1/2 here. So that 2 times 1/2 isn't changing this problem at all, but now I can just apply this situation here. So this is going to be 1 over natural log of 4, and that 1/2 is going to stay in front, times 4 to the x squared minus 1, and this whole thing is going to be evaluated from 0 to 1/2. I'm going to factor this scalar out, 1/2 natural log of 4, 1 over 2 natural log of 4. And then I'm going to use substitution here, 4 to the, if I plug 1/2 in, I'm going to get negative 3/4. If I plug 0 in, I'm going to get negative 1. And I'm going to go ahead and leave it there, unsimplified. So not a lot of times are you going to have to use this particular formula, but it's one of those things that when the opportunity arises and you have an exponential function, this is how you're going to integrate it. So now we're going to talk about the last sort of unique type of function that you might see or need to recognize how to work with when we're integrating, and that's inverse trig. So when we were learning about derivatives, we learned how to find the derivative of inverse trig, and we learned that the derivative of arcsine is 1 over the square root of 1 minus x squared, and we actually derived that. What we're now going to do is work backwards and say if we can recognize that derivative as our integrand, then that must mean our original function was arcsine. So we're using that pattern recognition. We know the derivative, so can we identify which derivative we have to work backwards? Because that's the whole idea behind integration. So we know that 1 over 1 plus x squared is the derivative of arctangent. So if we see 1, or dx in this case, over 1 plus x squared, that must mean the original function was arctangent of x plus some constant. Similarly for arcsecant. So if there is more going on than just 1 plus x squared, 1 minus x squared, if there's an a value, that's going to come into play in a similar way as it did when we were taking derivatives. So the key thing here is you need to be able to recognize when something looks like arcsine, when something inside the integral or the integrand, when it looks like arccosine, when it looks like arcsecant. The reason we only have 3 of these listed here is because the other 3 are just off by a sign, right? So the negative version of each of those integrals would give you the other 3 inverse trig functions. So our goal for the rest of this video and the rest of this practice in this section is really to be able to look at an integration problem and develop a strategy for integrating and then work through it based on that strategy. So I haven't separated these problems by all of them are inverse trig or all of them are ln or all of them are u substitution, because I want you to push yourselves to start thinking through how to evaluate each of these integrals using any of the tools that we have learned so far. So let's look at some examples. Okay, here are our first 3 problems. I'm going to encourage you to pause the video and just ask yourself, does this look like inverse trig? Can I use u substitution? Is there something algebraic that I can do first to simplify this problem? So make a strategy before you jump into integration, and then unpause the video and see how you did. All right, hopefully you had time to come up with a strategy. When I look at number 6, it looks like some sort of arc sign to me. When I look at number 7, I think that I could either use long division or I could rewrite this integrand by splitting up into 2 fractions. And that might be a good first step to help me, because this whole thing is just going to become 1, and I know how to integrate that. So that seems like that's going to be a good starting strategy. And when I look at number 8 looks an awful lot like some version of arctangent. So now that we've come up with a strategy, go ahead and pause the video, finish the integration, and then unpause the video and see how you did. All right, so number 6 is arcsine. If I integrate this, this is going to be arcsine of, well, the thing that's in the place where u is just x squared. So u squared is x squared, so u is x, over a, in this case, is 2. So arcsine of x over 2 plus c. So really you can think of this integral as the integral of dx over the square root of 2 squared minus x squared. That might help you identify your u and your a. Number 4, this first piece of the integral is going to become 1x when I find the antiderivative. And then this piece here looks like natural log, and it looks like I could just reverse the chain rule, and you're more than welcome to show u substitution if you need to for that piece. I'm going to just reverse the chain rule. The derivative of x squared plus 2 is going to be 2x, and I have 4x, so I have an extra 2 here. So this is going to be x minus 2 natural log of the absolute value of x squared plus 2 plus c. But again, if you wanted to use u substitution, you could let u equal x squared plus 2. So du is 2x dx. And that can help you see how to do that. Hopefully you're getting away from needing to do u substitution when you can reverse the chain rule. And number 8 is arctan. In this case, a is the square root of 2. And u is 3x. So this integral is going to equal 1 over 3 root 2 times arctan of 3x over the square root of 2 plus c. And that 3 in the denominator is coming from the derivative of 3x is 3, so I need an extra 3 in the numerator, which means I need a 1/3 in the denominator. Or, again, you could say, let u equal 3x, so du equals 3 dx, and you could rework it and see that arctangent relationship. So I'm going to give you a few more. I'm going to give you time to look through them, to come up with a strategy to integrate, and then go over them together. All right, so here are 6 more examples. I'm going to encourage you to pause the video and come up with a strategy for each of these problems, and then unpause the video and check out the strategies before you jump right in. All right, hopefully you paused the video. Number 9 looks a little bit like inverse trig, but the key difference between number 9 and the number 6 that we just did is that there's an x in the numerator, which actually means that regular u substitution or reversing the chain rule is going to work here. If I take the derivative, I get negative 2x dx, which allows me to rewrite this integral du over negative 2x like this. This is going to integrate from here. I'm not going to finish that, but regular u substitution looks like it's going to work there. On number 10, we have no idea how to integrate natural log, which automatically makes me jump to u substitution. So I'm going to assume that I'm probably going to let u be 2 minus ln of x. That's going to mean that du is negative 1 over x dx, or that negative x du equals dx. And then we can rewrite this integral as 1 over x times u to the 3rd times negative x du. And then we can finish that. For number 11, lots of e's going on here, but since I know that the derivative of e to the x is e to the x, I'm wondering if using u sub with u being the denominator is going to help me out here. This is going to give me e to the x minus e to the negative x dx, which is what the numerator looks like, e to the x minus e to the negative x over u to the 4th times du over e to the x minus e to the negative x. So those are going to divide out. Number 12 looks like arcsecant, so I'm going to encourage you to see, is there something I can use with arcsecant here? Number 3 looks like I can immediately just get ln. And number 4 looks like a problem where I might want to divide my polynomials first. So now that we have a strategy, I encourage you to pause the video and work through each of these problems all the way to see how you do, and then unpause the video. All right, for number 9, this x is going to divide out. So we have negative 1/2 times the integral of u to the negative 1/2 du. That's going to equal negative 1/2 times 2 times u to the 1/2 plus c. And then if I simplify and substitute back in what I know u is, this is going to be negative 9 minus x squared to the power of 1/2 plus c. On number 10 here, these x's are going to divide out. So this is going to be negative the integral of u to the negative 4th du. Sorry, u to the negative 3rd du. So if we integrate that, negative u to the negative 2nd divided by negative 2 plus c. And if we substitute back in, this is going to be 1/2 times 2 minus ln of x to the negative 2nd power plus c. On 11, these two things are going to divide out. So that's the integral of 1 over u to the 4th. Well, that's going to be equal to negative u to the negative 3rd over positive 3. Or u to the negative 3rd over negative 3 plus c. And then we can rewrite this out with u plugged back in, e to the x plus e to the negative x. All right, number 12 is arcsecant, and it's a little bit difficult to see without showing the u substitution. So I'm actually going to do that. I'm going to let u equal 2x, which means that du is going to be 2 dx. So I can rewrite this integral. This is staying the same. This 2 in the numerator is from the original problem. X times the square root of 4x squared is going to become u squared minus 9. So all I have changed so far, and then this is going to be times du over 2. So all I've changed so far is in purple. What I want you to notice is this 2 and this 2 are going to divide out. And I can't actually integrate this until I get rid of this x. So I need to substitute in something that I know to be true for that x. Well, if u is equal to 2x, that means that x is equal to u over 2. So I'm going to go ahead and put that in front. So now I'm here, and I want a u in front, so this is good. I'm going to take that scalar out. If I have 1/2 in the denominator, that's really the same thing as having 2 in the numerator. So I'm going to take a 2 out of my integral so that it's more easy to see the arcsecant that's happening here. There we go. So now we're going to get 1/3. So this 2 is going to stay in front. When I integrate to get arcsecant here, we're going to get 1/3 times arcsecant of the absolute value of u over 3 plus c. And actually, I'm going to put the plus c on the outside. So now I'm going to put what I know u is. U is 2x. I'm going to put that back in, and I'm going to multiply my 2 through. 2/3 arcsecant of the absolute value of 2x over 3 plus c. Okay, number 13 is just going to be 3 natural log of the absolute value of x, evaluated from 1 to e squared, which is going to be 3 times the natural log of e squared, which is going to be 2, minus natural log of 1, which is 0. So this is just going to be 6. All right, I'm going to go ahead and do long division, or actually I'm going to use synthetic division, because why not? Negative 1 into 1, negative 3, 0, 2. I'm going to go ahead and work through this. That's going to get me here. So I can rewrite this, and I'm running out of space, so I'm going to come down here. I can rewrite this as the integral of x squared minus 4x plus 4 minus 2 over x plus 1 dx. And then I can find that antiderivative just using the power rule. I don't really feel like simplifying today. Minus 2 ln absolute value of x plus 1 plus c. So I'm going to give you 3 more, and they're all, actually 2 of them are a little bit trickier. So let's see how you can do with 3 more problems. All right, go ahead and pause the video, come up with a strategy, and then work through it on your own and see how you do. Then unpause the video, and we'll go through them together. All right, hopefully you had time to work through these. What I'm going to do on number 15 is I'm going to use u substitution. If I try to let u just equal e to the 2x minus 1, when I take the derivative of that, I'm going to get 2 times e to the 2x. And that isn't really, it seems like something's going to be a little bit off here. So I'm going to see what happens if I just let u equal e to the x. Because if I'm going to take the derivative and I'm still going to have something related to e to the x, and there's a square root, that kind of feels like arcsecant a little bit. So I'm going to let u equal e to the x, which means that du is e to the x dx, which means that du divided by e to the x is dx. And then I'm going to rewrite my integral. This is going to become 1 over the square root of u squared, e to the 2x is u squared, minus 1 times du over e to the x. What this means is that I can substitute this in for what I know it's true, it's u. So this is 1 over u times the square root of u squared minus 1 du. Now I think it's really obvious that this is arcsecant. It wasn't at the beginning, but trying regular u substitution with what's inside the radical wasn't working. So I tried a little bit different method, and I got arcsecant. So this is going to be equal to arcsecant of the absolute value of u plus c, or arcsecant of the absolute value of e to the x plus c. Number 16, I'm going to use a little Algebra 1 skill to rewrite this. I'm going to complete the square in the denominator. So this is going to be x minus 2 squared plus 3, if I complete the square there, which means now I have the sum of 2 squares, which is screaming arctangent to me. So this is going to be 1 over the square root of 3 times arctangent of x minus 2 over root 3 plus c. Now we're going to talk about in the next video on partial fraction decomposition different strategies for when you see a polynomial or you see a rational expression, how to approach that. That's going to come up in more detail in 4.8. Okay, last but not least, we can use regular u substitution. So if we let u equal sine of x, then du is cosine of x dx, and that's in the numerator. So I'm going to need to change my bounds here. If x is 0, when x is 0, u is sine of 0, which is still 0. When x is pi over 2, u is sine of pi over 2, which is 1. So I get to change my bounds to be in terms of u, which means I never have to convert back to x here because this is a definite integral. This is cosine x over 1 plus u squared times du over cosine of x. So the cosines are going to divide out. And now I have 1 over 1 plus u squared, which is arctangent. So this is going to be arctangent of u evaluated from 0 to 1. So this is going to be arctangent of 1 minus arctangent of 0, which is going to be pi over 4. So a lot was covered in this video. We revisited and practiced a little bit more with natural log and with integrating with e, and we used that to determine and to prove how to integrate exponential functions that are of base other than e. Then we acknowledged the relationship that we already know about the derivative of inverse trig and how integration and derivatives relate, so that we could identify those patterns when we're integrating something that the integrand looks like inverse trig. Then we put that all together and we just worked through a bunch of different integration problems to try and test out those strategies. So go ahead and write down any questions you have, and I look forward to supporting you on this. Thanks for listening.